Hi everyone, thank you for joining my talk. In the next 25 minutes, I will talk to you about the Fritzfrog campaign, which is a fascinating campaign we uncovered in Guardicore Labs around 3 months ago in August. A couple of words about myself. I'm a security researcher at Guardicore Labs. I do malware analysis and reverse engineering, and I enjoy learning and practicing low-level topics like operating systems, binary exploitation, and more. I wrote an online tutorial, which is also free for whoever wishes to start reverse engineering. You're welcome to give it a shot and tell me what you think. And you're also welcome to follow me on Twitter. This is my handle, my full name. When did we first meet Fritzfrog? So around April, we started seeing attack incidents in our sensors. I will talk a little about them in the end of this talk. All attack incidents bear the same format. So the attacker breached our sensors over SSH using brute force. Then two files were downloaded and executed, ifconfig and nginx. The two were actually the same file with the same hash. It was a Golang binary, which was not recognized by any engine such as VirusTotal, VirusPay, etc. The process started scanning multiple IP addresses over SSH ports and also started listening on port 1234. The fact that the malware file was unknown made it quite interesting for us, so we signed this campaign based on the process names and we started monitoring its activity. And we found a campaign on the rise, actually. It started in January of 2020, and it just very rapidly, it was increasing in the number of attacks. We saw hundreds and even thousands of attacks per day only on our sensors. So there were probably many more attacks going on, and we figured this must be a huge scale campaign. So we decided to take a deeper look into both the malware and the attack chain itself. And looking at the flow in the incident in our sensor, we noticed this unusual command, the netcat localhost 1234. If you remember, the malware itself was listening on this port. So something was trying to connect to the malware, which acted as some kind of server. And the malware responded with a base64 string. I looked at different attack incidents, and this response was different every time. Of course, I tried to decode the string, and it resulted with nothing readable. So this was probably binary data encoded. This seemed very interesting to me. I wanted to understand what this netcat command line was about, and the base64 seemed like a good entry point. So I took the malware file, I debugged it, I put a breakpoint on the base64 function, and I let the malware execute, while in a separate terminal I ran netcat localhost 1234. And the malware luckily immediately hit the breakpoint, resulting in this beautiful call stack that you see right here. So the base64 function was actually called from within a Diffie-Hellman key exchange function, which was in turn called by functions named new crypto communication from buffer or connection. And at the top of this execution chain, there was a function called worker, and it had no parents, so I figured this was executed as a Go routine. Reverse engineering the flow a bit deeper, I understood that the communication sequence was as follows. The client connecting to the malware was expected to send its public key, base64 encoded, and the malware responded its own public key, also base64 encoded, which is exactly what we saw here. This is a public key of the malware, which is encoded and returned to the client. According to the Diffie-Hellman protocol, the two sides now derive their own shared secret, which in our case is an AES encryption key. And from now on, communication is encrypted using the symmetric key. So the client can send its command encrypted with the symmetric key, and again, base64 encoded, and the malware sends the response in the same manner. This was really nice, but of course, my next question was, what is it for? Why do we exchange keys? Why do we start communication? And what are the commands that are supported in this type of traffic. What is the malware expecting to receive? I went to the worker function in the disassembly. This is cutter, this is radar GUI, and the key exchange appears exactly where the arrow points. After the key exchange takes place, as we said before, the client sends its command, encrypted command. The malware decrypts this input and then compares it to several different strings. Each branch here in this function corresponds to a command that the malware supports and dispatches further to another function. So I zoomed in on each branch and I kind of constructed a set of commands that the malware supports. And this was a resulting set. I tried to classify the commands into several categories: database, payloads, and administration. Each one of them had some interesting artifacts. So the database operations taught me that the malware could send and receive databases, either zipped or not. And there was also some kind of target management. The malware could push and receive targets and also force targets on other instances maybe. With regards to payload operation, there were capabilities of running scripts, running different binary payloads, and sharing files. And actually, the most intriguing part was in the administration operations, where we saw get blob stats, get peer stats, and get vote stats. And this terminology, the term peers, I was not very used to seeing that frequently in my investigations of botnets. So this kind of raised my eyebrows. So I tried to look at the bigger picture. There was no single command and control server being connected to, and actually there was not even a set of different C2s connected to by the malware. There was peer functionality going on with database exchanging and file sharing as well, and there was massive SSH scans that you saw yourself at the beginning. All this led me to understand that Fritzfrog was two things. First, it was a peer-to-peer botnet. Every node was its own C2, being able to receive and send commands to other nodes. No single point of infrastructure. And the second thing Fritzfrog is an SSH worm. So we try to replicate the malware to other SSH servers, thus expanding the whole peer-to-peer network to other machines in the internet. With this understanding, actually, the research process became somewhat easier because suddenly the module names started to click and the sequences started to make sense, and really this helped us get our way through the malware. First, before we get into the specific details of Fritzfrog, what are the benefits of a peer-to-peer network? So perhaps many of you can guess, but a decentralized infrastructure is harder to attribute and take down. And actually, all the data is shared among the network. So there's always backup. You could see yourself that nodes can exchange databases and files. So there's always backup, and there's no single point of failure. If one node fails to execute, others will take over instead. At some point, we were able to intercept the traffic. I will elaborate on that later on. But the thing with peer-to-peer is you can't really understand where commands are coming from in the first place. So you can see commands being sent in the network, but we couldn't really attribute the commands to the first node initiating them. And now let's dig deeper into the infection process. So we used to call instances running the malware, we call them frogs. So let's imagine a frog in the network. We can also refer to it as an attacker node. This attacker node brute forces SSH servers and tries to breach them. Once it manages to find a successful pair of username and password, it establishes a SSH session with the new victim and copies and runs the malware on the remote host. Using the same SSH session, the attacker node establishes another peer-to-peer channel, not the SSH one, but one over port 1234. And it does that by running netcat localhost 1234, the command we saw at the very beginning of this slide deck. If we want to see that more visually, let's take a look at this graphic. Initially, we have only the attacker node with the malware running on it. The attacker node manages to breach a new SSH server in the internet, and it copies the malware onto the new victim and runs it there. Now there is an active SSH session going on between the two ends. And over this session, the attacker node runs netcat localhost 1234. So what I want to emphasize here is that the netcat client actually runs on the remote victim. So it connects to whoever listens on port 1234 on the victim, which is the malware. Now at this point, the attacker node can send any command that we saw from the command set before. It can send get log, get status, get peer stats, get blob stats, and this will reach the netcat client. It will actually be the input of this netcat client and then directed to the malware over port 1234. So the thing I'd like you to notice here is that if I'm a firewall here, standing right here in the middle, all I see is standard SSH traffic. I don't see any traffic being done over port 1234 because this traffic only takes place on the victim node on the local host interface. So this is a really nice way to kind of evade firewalls and their basic rules, assuming that this firewall allows SSH traffic. This was zoom in on a single infection process, but it's important to remember that the whole network is engaged in this brute force effort, and the attack force is much bigger this way. Now, what's interesting about Fritzfrog is that it's very intelligent in the way that it manages this attack force. We noticed that no two nodes ever target the same IP address. There's no intersection between the target lists of two nodes in the network. And we suspect that the module responsible for this very smart management is cast votes module. This module is responsible for maintaining a voting system where eventually it reaches a consensus about a winner node in the P2P network. And this winner node becomes responsible for target distribution. It tells each node which targets to attack. This is a kind of a macro look at the brute force attempt, but even at the node level, every node runs multiple threads of the cracker module, which is the brute forcer. So Fritzfrog really puts a lot of effort into using a lot of resources for this brute force attacks. You can see here a piece of Fritzfrog logs where we see different cracker threads performing brute force on various targets. Another interesting aspect of the Fritzfrog network is the way in which it transfers files between the nodes. So it uses a torrent-like file transfer mechanism where files are never transferred in their entirety. They're transferred in blobs. And blobs are pieces of binary data which comprise a binary file as a whole. Now each node keeps a mapping between the nodes that it has available to it and their hashes. And when it wishes to run a file, it needs to make sure first that it has all the necessary blobs. And then a special designated module called assemble takes all these blobs, concatenates them in memory, dumps them onto a file, executes this file, and deletes it immediately. What you see here at the bottom of the slide is the blobs available to a certain node in the network, which we gathered by sending this node the getDB command. A nice use of the assemble module can be seen in the cryptominer module. Fritzfrog runs a Monero cryptominer, a compiled version of XMRig, and the module responsible for the crypto mining is called libexec. I just want to emphasize that this module is capable of running basically any binary file. The miner is not hard-coded to the Fritzfrog malware. What you see here on the right is a loop where assemble file is called repeatedly to assemble the whole cryptominer binary file. Eventually, like I mentioned before, it dumps it onto a file, executes, and deletes it. And also with regards to malware, very similarly to other malware families, Fritzfrog is also quite competitive. So it's not sharing the local machine's resources with others. There is a designated module called antivirus, which periodically checks for the process list and sees if there are any CPU demanding processes running. If there's such a process, which also has the XMRIC substring in it, then this process is terminated immediately, and Fritzfrog keeps the CPU computing resources to itself. Now to the fun part of the research. At that point, we understood the whole command set of the malware. We could mimic the key exchange process, and we could basically perform communication with frogs in the wild from end to end. So we thought with that knowledge and ability, we could understand the scope of the campaign, how many targets there were, how many actual infected nodes, and this is what we set out to do. We decided to write our own tool that we named Frogger, and we used Golang, of course, to speak to the attacker in their own language. We also used the same libraries that the malware used, and fortunately we have these in the Golang binary because they're statically linked and their file names and paths are saved quite clearly. So we use the same formatting libraries, as you can see here. We use the same Diffie-Hellman key exchange library, which is of course also open source. But we also had to use the same representations and the same data structures that the malware was using. One of the things we wanted to do was to inject our own SSH server to the Fritzfrog network. And to do that, we had to kind of tell one of the nodes that there's a new breached SSH server which can be infected. To understand how such nodes or such victims were represented, we sent a getDB command to one of the nodes in the wild, and in return we got the full database, part of which was the representation of deploy entities. A deploy entity is a successfully breached SSH server, which was not yet infected with the malware. We took this data structure and integrated it into our code. Of course, we replaced all the members with our own machine details. And eventually, we sent a put deploy command to one of the frogs with our own server in the payload. And this was actually one of the most exciting moments of the research because just seconds or minutes after we did that, I saw the malware process running on our SSH VM, which meant the process was successful and we managed to inject ourselves into the network. Now regarding targets, being able to talk to other nodes allowed us to understand the scope of the campaign. So we took all the nodes we knew of and we asked each of them for their target list. And we constructed this enormous target list with millions of targets around the world and put it on a map. As you can see here, the targets are mostly in the US, in Europe, India, and South Korea. And the sectors also vary. We saw targets in the educational sector, many universities around the world, the financial sector, and even healthcare organizations. Apart from targets, we also wanted to know how many of them were actually breached, how many nodes actually ran the malware at some point or another. So we took all the IP addresses that attacked our sensors. There were, I think, about 100 of them. We also looked on Shodan for machines listening on port 1234, and we fine-grained our search to only 124 bytes responses because this was the response length from Fritzfrog malware, the public key base 64. And then we took this initial set and we asked each node for its peer list, and then we did this recursively. So we ended up crawling the whole network, and one of our more successful days, we managed to produce this cluster of around 80 nodes. But overall, we saw from the beginning of the campaign around 500 infected nodes in total. There's always a possibility that there were even more nodes and that we were simply not able to reach other clusters. So there might have been even more infected SSH servers that we did not spot. One last thing I want to show you that we were able to do with our Frogger tool was to see the representation of file availability in the network. So for example, here we take a frog in the wild and we send the get blob stats command. We first connect to this frog over port 1234, which is the peer-to-peer port, and we send the get blob stats. In return, we get this beautiful matrix where every column is actually a file. You can see here the list of file names. Many of them are just the malware binary compiled for different platforms, but this one is the libexec file is the crypto miner. So for example, we have a breached node here. We have a peer in the network. Its credentials are tbox. And in the column that corresponds to the crypto miner, it has only 3 out of 4 blobs. So it cannot really run the miner, and if it wishes to run the crypto miner, it needs to first ask its peers for the missing blob, and then assemble all the blobs using assemble module and run it locally. So these were the technicalities of Fritzfrog, but one might wonder what makes it special, because Fritzfrog is not the first P2P botnet seen in the wild, and it's not even the first one to be used for crypto mining. So what makes it special? I think Fritzfrog is special compared to other botnets in the fact that it combines several characteristics that no other botnet combined in the past. And these are those characteristics. First of all, the peer-to-peer protocol itself is written from scratch. We did not see any code reuse, we did not see any existing libraries being used or even existing protocols. This looked like a very, very new protocol being developed by very talented people or maybe person from scratch. Second thing is that the malware is sort of fileless. It's not completely fileless, but it does write files on the file system, but it makes sure to delete them very, very immediately. So there's no long-term traces on the file system showing that Fritzfrog was actually there. Also, there's no working directory in the sense that logs are not saved locally, but always kept in memory. The brute force attempts are aggressive compared to other botnets. Some of you may know DDG. It's a quite famous peer-to-peer botnet used for crypto mining. And even DDG, which is very powerful, it only targets the root username. Fritzfrog uses dozens of different usernames. You could see some of them in the screenshot from a couple of slides ago. And it uses countless of passwords, so its brute force attempts are much more aggressive. However, it still is efficient in its brute force attempts and in the way that it distributes targets. And we've talked quite a lot about that before, but really you can tell how much Fritzfrog cares about the resources that it has, and it's making sure not to waste these resources and really make very intelligent use of them. One last thing I want to talk about is the ultimate goal of Fritzfrog. Now, this is kind of a personal note, my personal thoughts on Fritzfrog's goals. I have to say that by looking at the number of wallets used and the money made of this campaign, it looks as if crypto mining is not the focal point of the malware authors here. What I think is that a group of people developed a very, very complex system, which is a peer-to-peer as a service platform that they can offer to other attack groups and gangs for their own purposes. So this peer-to-peer as a service can be used for malware deployment, ransomware, DDoS, and of course just gaining access to SSH servers, which is also profitable today. These are just my thoughts. If you wish to learn more about how we collect information on threats, what are the insights that we gathered from looking at data center targeting threats, you can actually look at the slides from last year BotConf, where Daniel Goldberg and myself gave a talk. Also, I invite you to take a look at our Botnet encyclopedia. This is quite a recent project that we put up, and this is where we share information about new and past botnet campaigns that we see. So we will be very happy to hear from you, collaborate, hear some feedback, and just talk about these threats. I'd like to thank you once again for your time and attention. This is the time for questions. If you want, you can ask now or later on Twitter. So thank you.